Our next speaker is Ariana from UC Riverside. She'll be speaking today from JWST to Roman, a physics-informed AI super resolution framework for Grism spectroscopy. Okay, take it away. Thanks.
Hello everyone, I'm Ariana Haghjoo. I'm a PhD student at UC Riverside, working with Bahram Mobashir and Shubhana Hemati here at Caltech IPAC. And today I'm going to talk about this AI framework that we have built for spectral super resolution and how we transferred that framework from JWST to Roman. So first of all, let's quickly have a recap of why we actually need high resolution spectroscopy. We know that the amount of information that we can recover from any kind of astronomical data is bound by its resolution. And if we have a high resolution spectra, we can deblend lines that are close together in wavelength space. And this gives us access to precise redshifts and line fluxes. Having this exact line fluxes will give us much more information in terms of the diagnostics of galaxy evolution, SFR, dust measurements, metallicity, agent activity, or even electron density. And also having accurate redshifts helps us in our cosmological studies, such as galaxy clustering and weak lensing. In contrast, if we only have access to low resolution spectra, we will lose a lot of information, and this limits the amount of scientific data that we can actually get from our observations. So the challenge here is that if we want to do a statistical studies, we need a large sample of spectra, but we know that getting high resolution spectra is time-consuming and expensive. So this is the reason that deep surveys such as Euclid and Roman are focusing on collecting large amounts of data sets, but in lower resolution of spectral resolution, and this is a major information bottleneck. So what should we do here? One of the solutions to this problem is to train an AI model to learn the mapping between the low resolution and high resolution spectra, and then use this mapping later to inference as inference. So what we do is that if we have access to a data set that has observed the same galaxies in low resolution and high resolution, we train an AI model based on these two, and then the inference here can be used for low resolution data that we don't have access to the high resolution one, and then transfer this low resolution to the high resolution counterpart. And this is exactly, This is exactly where the Euclid and Roman Grism spectra come into the picture. If we build this AI model, we can use it to convert the Euclid and Roman Grism spectra to high resolution. So the pilot study was done using JWST near-spec data from JADE survey. JADE survey gives us access to two different resolutions, the prism resolution, which is approximately R of 100, and the medium grating, which is R of approximately 1000. This survey covers the good north and good south fields on the sky, and the prism spectra is merged completely and comes prepared. However, for the medium resolution, it comes in three different patches, three different gratings. These need to be added together. Some of the gaps, such as here, needs to be predicted using different methods. And you also need to change the grading of the prism one and bring that grading to the grading of the medium resolution. And then one final step before you train your AI on this is that you may want to introduce some quality cuts, because if you have very bad spectra and then you train an AI model based on that, the model is going to learn noise, and you're risking hallucinations in the predictions, hallucinating features that don't actually exist in the real spectra. So that's why we did this quality cut. We only chose a spectra that had basically one important emission line, one significant emission line, H alpha O2 or O3. And after this quality cut, we were left with approximately 1,200 pairs, which in terms of AI stuff, it's not enough for training a healthy model. So what we did was that we introduced an augmentation technique, making new copies of data, perturb new copies of data. We did introduce some redshift perturbation and also some flux perturbations, 10% of noise on flux at each point. And then after this step, we basically made 20 copies of each of the spectras. And after this step, we remained with approximately 25,000 pairs, which gave us a healthy data set in terms of the size and diversity of noises and line positions. Just like any AI studies, we had to explore many different architectures to find the one that works for our problem. The one that we chose was that it's a 3-step model. The first step is a conservative super resolution. It sits very close to the low resolution spectra to make sure that we are not hallucinating any features. The second step is a redshift prediction. It's again a very simple CNN model that predicts a redshift. And the final stage here, or SR2, SR2 is a transformer or attention layer. And because it actually knows the redshift from the first step, it can now focus on a specific windows in your spectra that you expect to see important features, important emission lines. So it goes and refines those, this SR2 step here, it goes and refines those features for you to finally give you the complete super resolved spectra. So some results from our predictions here. As you can see, the dotted red line here, this one is the Prism spectra. In the Prism spectra, the 2 O3 lines were completely blended together. The purple one shows the high resolution spectra that has deblended these two. And the orange line here shows our prediction that has effectively denoised and deblended these 2 lines from each other in both of the examples here. So we need to evaluate the predictions from our model because any generative AI model, the results need to be evaluated. So we had to invent our own evaluation techniques. One of the techniques that we introduced was checking the signal to noise of the predicted lines. Here we are looking at the prediction of signal to noise compared to the actual signal to noise in the low resolution input for the H-alpha, H-beta, O2, and O3 lines. And as you can see, in comparison to the low resolution input, we are seeing a very obvious boost in terms of the signal to noise of these lines. Also, we can look into the redshift prediction of this method. Redshift prediction is not exactly a final result of our method. Our method is not fine-tuned for redshift prediction. It's just a middle step for us. However, still knowing that, if we have a simple CNN that predicts redshift from the input spectra and use that network on all the low-resolution, super-resolved, and high-resolution sample, and compare the predicted redshifts with the actual redshifts from the medium-resolution catalog of Jade survey, as you can see, the outlier rate for the low resolution here is around 16%. For the high resolution is 0.5%. And our super resolved spectra, the outlier rate is 12.5%, which sits much closer to the high resolution compared to the low resolution. So our super resolved spectra has actually gained more information in terms of redshift compared to the low resolution input. However, we didn't stop here for evaluation. We wanted to know that, okay, we have spent like a significant amount of computation time on training this AI model. Are we actually gaining something compared to traditional denoising techniques that astronomers used before we had access to these AI techniques? So that's why we benchmark our model with 8 different classical techniques, such as the Richardson-Lussiv, the Wiener method, the Tikhonov, or even combining the Wiener with matched filter. And the results are pretty interesting. Here we see the mean absolute error, the uncertainty normalized error, and also the RMS. And as you can see, the ML1 has a very significantly lower predicted error on compared to all of the other methods. It's actually at least 30% better compared to the best classical model. Another interesting result is looking at the FWHM of some of the predicted lines. We again look at the H-alpha, H-beta, O2, and O3. And as you can see, the bias on the FWHM, how much actually the width was predicted correctly, the bias is the lowest amount for the ML method. There's also another interesting result here, and that one is the comparison between the Wiener method and Wiener plus matched filter. So the difference between these two is that the matched filter has access to the physical priors, the redshift, and also the line catalogs of all of these lines. But however, in the evaluations, we see that these two methods are not that much different with each other. What does this mean? It means that just introducing that physical prior doesn't close the gap between the classical methods and machine learning methods. The machine learning method is actually learning more than just these physical priors. So that's why the results are significantly different from these two methods. Okay, here. So now, let's try and transfer this framework to Roman. This is very preliminary results from these techniques. We have just started working on Roman simulations. The issue here is that Roman is going to give us tens of millions of Grism spectra at R of approximately 400. However, the bandpass is much narrower compared to JWST. It's just between 1 to 1.93 micrometers. And most galaxies only show one significant emission line in this region. And that's why the model actually kind of struggles to find out the correct redshift here, because it can't find out which line this line is here. What we needed to do was adding the photometry here. But the photometry is able to help us to break the degeneracy. So we have the same three-step architecture, the SR1, the photometry step, and the SR2 attention layer step. However, this time the photometry is being added to the redshift step here. The simulations that we used that included both of that could potentially give us both of the photometry and spectral data was the Open Universe 24. And the Open Universe 24 gives us access to SEDs, to light profiles, to dust, and to photometry, to dust information and photometry. And then based on these data, we were able to predict the realistic two-dimensional spectra using the noise models from Wang et al. Grism simulations. And then we used Grizzly to extract the one-dimensional spectra from these two dimensions. And then now we have photometry from here, we have extracted the spectroscopy, and then we can put it in this whole pipeline to get the super resolved spectra. Here again, we see the quality of redshift prediction, which is pretty good actually. In the same metric that we used for JWST data, here we have effectively 0% of outlier rates on predictions of redshift. And again, we look at the emission line recovery quality, and we again see a very significant boost in terms of the signal to noise of important lines. And with that, I leave you with my summary, and I'm open to your questions.
Hey, thank you very much for the talk. That was interesting. We have questions? Let's get the one in the middle there. Sign up for coming there.
So thank you for the very nice talk. So if I understood correctly, you are matching like low resolution spectra and high resolution spectra measured by different instruments for the same object. And then you are like building your training data set like this, right?
We are not actually mixing two different instruments in one training. So we did a training for JWST, then we did another completely different training with another completely different data set for Roman. So we are not mixing the data sets between these two.
Okay, but my question would be like, could you use like only the high resolution spectra and then somehow degrade the resolution to use this as input? Because that way you would have like more data to use in your training data. I don't know if...
If I understand your question correctly, you're asking like where the high resolution data is coming from? Or?
Yeah, get all the high resolution data you can and then degrade the resolution, use this as input. Is this what you're doing or?
No. We are not degrading the high resolution spectra by hand because the risk in doing that is because you will use a function basically to degrade your high resolution spectra. However, the model is smarter than the function that you use, and instead of learning the physics, it's just going to learn that mathematical function. So we don't do that actually. For the JWST spectra, we actually use both the observational low resolution and the observational high resolution. For the Roman one, since we yet do not have access to the observational data, our high resolution target is the SED, our low resolution is the simulated Grism spectra that has realistic expected noise from Roman.
Okay,
SED
perfect.
plus that expected noise.
Perfect, thank you.
Okay, we had a question right here.
Thanks. This is really exciting. I'm wondering about the photometry that you used to correct your redshifts. How many bands did you use? Sorry if I missed it.
Let me go back to this slide over here very quickly. We used 14 bands of photometry that came from this Open Universe 24 simulations.
And so do you have any thoughts on how we might do with Roman data when we have ancillary photometric data for Roman? Because I don't think it'll be 14 bands.
Yes, this simulation actually gave us like Roman plus Rubin photometries. So you're correct, for the actual Roman one, it's going to be less. But I think even having access to, I don't know, much lower numbers of photometry, this is going to work because you just need that for breaking the degeneracy on redshift. You're not using the photometry for the actual task of super resolution. You're welcome.
Okay, any more questions? Anything online, Tiffany? Okay, let's give Fawn a round of applause. Thank you very much.